Dear students, today I am going to discuss about the economical operation of the system. The economical operation of the system. So a properly designated and designed power system should meet certain requirements. So first requirement is the system should be able to meet the load demand changes. The load demand changes. So this load demand is not constant throughout the day. It varies from time to time. So a properly designed power system should be able to meet this continuously changing in load demand. And other requirement is the system should supply energy at minimum cost. At minimum cost. So economics are always important. So the supply of energy should be at minimum cost. Third requirement is the quality of supply. The quality of supply. So this quality means the system voltage and frequency should be maintained within the tolerable limits. The system voltage and frequency should be maintained within the tolerable limits. Generally, for voltage, the tolerable limit is plus or minus 5%. For frequency, the tolerable limit is plus or minus 1%. And the level of reliability of the system, the level of reliability of the system should be high. Should be high. So these are the important requirements for a properly designed power system. So this economical, the cost of energy is should be minimum. So that is called the optimal operation or economical operation. So this optimal operation of the power system is divided into two subproblems. One is called unit commitment problem. One is called unit commitment problem. The other one is called economic dispatch. The economic dispatch or load scheduling problem. Economic dispatch or load scheduling problem. So in a thermal power plant, there will be number of units for operation. So the running all the units for all the time is not economical. So keeping in view of the load demand, some of the units may be operated, some of the units should not be operated. So then the selection of number of units for optimal operation is called the unit commitment problem. So in other words, in the unit commitment problem, the number of units are selected for optimal operation. So which units have to be selected? That is the unit commitment problem. So what is the objective? Again, the cost of generation, minimum cost of generation is the objective. So with that objective to determine the number of units for operation is the unit commitment problem. So the economic dispatch or load scheduling problem means once the units are selected for optimal operation, how to allocate the load among the selected units is the load scheduling or economic dispatch problem. So like that, the optimal operation is divided into two subproblems. So before going into this economic dispatch problem, it is necessary to discuss certain important characteristics of the thermal plant. One important characteristic is the heat rate characteristic. Heat rate characteristic. So this heat rate characteristic is a plot of heat rate. A plot of heat rate versus the power output. A plot of heat rate versus power output. So this heat rate is generally expressed in kilocalorie per megawatt hour. Kilocalorie per megawatt hour or British thermal unit per megawatt hour. The power output is expressed in megawatt. The plot will be like this. So a minimum limit will be there and a maximum limit will be there. And other characteristic is the input output curve. The other characteristic is input output curve. So this input output curve is a plot of the fuel input, is a plot of fuel input and power output, is a plot of fuel input and power output. So this fuel input is expressed in kilocalorie per hour, kilocalorie per hour, or British thermal unit per hour, kilocalorie per hour or British thermal unit per hour. The power output is expressed in megawatt. This input output curve is concave upwards. So this input output curve also has the minimum limit and maximum limit. So the significance of this heat rate characteristic is once the heat rate characteristic is known, the input output curve of the thermal plant can be drawn. Suppose the heat rate is H, the power output is PCI, then the fuel input equal to the heat rate into power output. So like that, once the heat rate characteristic is known, the fuel input can also be calculated. So suppose the cost of fuel is K rupees per kilocalorie. Okay, the cost of fuel is rupees per kilocalorie. Then the input fuel cost equal to the cost of fuel into the fuel input. So the cost of fuel is K rupees per kilocalorie. Then the input fuel cost C equal to the cost of fuel into fuel input. The other important definition is incremental fuel rate, the IFR. That means incremental fuel rate. Incremental fuel rate. So this incremental fuel rate is the ratio of change in input to the change in output. It is the ratio of change in input to change in output. The shape of incremental fuel rate will be like this. Incremental fuel rate is plotted on y-axis. The power output is plotted on x-axis. So this is the incremental fuel rate characteristic. So once the cost of fuel is also known, then we can get the incremental fuel cost. Incremental fuel cost. So this incremental fuel cost is the cost of fuel into incremental fuel rate. Into incremental fuel rate. So the incremental fuel cost characteristic will also be like this. So incremental fuel cost on y-axis and the power output on x-axis. So this incremental fuel cost units will be then rupees per megawatt hour. Rupees per megawatt hour. The power output is expressed in megawatt. Then one more definition is incremental production cost. Incremental production cost. So this incremental production cost, so generally, so it can't be calculated ideally. Therefore, it is generally taken as some percentage of incremental fuel cost. So we can write this one as the incremental fuel cost plus some percentage of incremental fuel cost. So this some percentage, this includes some running expenses, some running expenses. So these running expenses include labor charges, cost of labor like that, water, maintenance cost, all this. So the incremental fuel cost plus some percentage of incremental fuel cost is called the incremental production cost. So generally the cost expression is taken as a linear expression for our ease of analysis. So the standard representation of this cost function is like this. AI plus BI PZI plus CI into PZI square, where CI is the cost, fuel cost, or it is called the input fuel cost. AI, BI, CI are the coefficients. PZI is the power output expressed in megawatt. Once the cost expression is known, then the incremental fuel cost is the first derivative of this input fuel cost with respect to PCI. That is DCI by DPCI is called the incremental fuel cost. So then the expression will become BI plus 2 into CI PCI. So this is the incremental fuel cost. So generally it is the cost curve, as I told, is taken as a linear curve for our ease of analysis. So the objective of this optimal operation is to get the minimum cost. So in solving this objective function, we have to consider some constraints also. Some constraints, that means some limitations also we have to consider in solving this objective function, or to get the minimum cost of generation. We have to consider some of the limitations or constraints. So these constraints are generally classified into two types. One is called the equality constraints and the other one is called the inequality constraints. Equality and inequality constraints. The equality constraints is nothing but the load flow equation or power flow equation, or generally this equality constraint, we write it as the power balance equation. What is the power balance equation? Generation equal to load demand plus losses. Load demand plus power losses. That is the equality constraint. So these inequality constraints, the inequality constraints consists of generator constraints and voltage constraints. Generator constraints and voltage constraints. So again in the generator constraints, for active power generation, there is one constraint. Reactive power generation, there is other constraint. So first we will see what are the generator constraints. So the generator constraints are: the source is limited by thermal consideration. So then minimum power generation is limited by the flame instability. So that is the active power generation should be within its minimum limit and maximum limit. Within its minimum and maximum limits. So the maximum power generation is limited by thermal consideration and minimum power generation is limited by the boiler flame instability like that. Similarly, for reactive power generation also, there is some minimum limit and maximum limit. Some minimum limit and maximum limit. So the reactive power maximum limit is limited by the overheating of the rotor, and minimum limit is imposed by the machine stability limit. So like this, for generator constraints for active power generation, reactive power generation, certain limitations are there, minimum and maximum limit. Then voltage constraints. Voltage constraints. So these voltage constraint means the magnitude and phase angle of the voltage at various nodes should vary within the limits. Should vary within the limits. So the magnitude of voltage at various nodes should be within its minimum and within its maximum limit. Similarly, the phase angle also should be within minimum and maximum limits. In the next video, I will discuss about the economic operation for various cases.